Сейчас, одну секундочку, да. Ну все, запускать можно? Да, сейчас я... Так, а оно работает?
Да, уже не работает.
Работает, да? Well, we are going to start today's lecture. So I recall that last time we stopped approximately at the following point, that if we have a surface which is genus G compact surface minus n punctures, then and suppose that we have a hyperbolic metric on it, and I say I want to say once more, and then I always implicitly mean this, that hyperbolic metric is always finite area and complete. This is automatically true, both are automatically true if we have no punctures, but if we have punctures, then we should restrict ourselves to finite area complete metrics. And once we have such situation, then the universal covering is always isometric to the Lobachevsky plane, to the whole Lobachevsky plane. This we have discussed this last time, that these two conditions guarantee that it is the whole Lobachevsky space rather than a region in it. Since we have this, the fundamental group of the surface acts by deck transformations on the Lobachevsky plane, acts by isometries. To be precise, this is not well-defined object. A well-defined object is a fundamental group with chosen base point. And now I just would like to recall that the action is like that. If we have here S, and we have here something like, okay, it is very not so easy to draw a covering over surface, so it is some schematic picture. So if we have here some x0, and we may choose its preimage x0 tilde, and once we have some loop gamma in the base, then we can choose a preimage of this loop. We can lift this loop so that it starts in x0 tilde, and then it finishes in some at some point, and there is a unique deck transformation that takes x0 tilde to this final point. There is unique deck transformation. This is and the only thing which we should be careful about is okay. So this is let it be, since the deck, let it be d gamma. The only thing we should be careful about is whether this correspondence gamma to d gamma is a homomorphism or an anti-homomorphism. it is not so important, but we should be careful. Once we have this loop gamma and another loop delta, okay, then if we are interested, if we would like to consider a loop gamma delta, so we first go around gamma and then around delta, then its lifting is as follows. We first take lifting of gamma and then we take lifting of delta, but starting from this point rather than from x0. So if we have lifting of delta from x0, this delta tilde, then this lifting is obtained from that by this d gamma. So this one is d gamma of delta tilde. Okay, and what is this point? We are interested. What is this point? Is it d gamma d delta of x0 tilde or vice versa? Okay, we see that that point is d delta of x0 tilde, the finishing point of delta tilde, and so this is obtained by d gamma. So this is indeed d gamma d delta of x0 tilde. So this is not an anti-isomorphism, but it's a true isomorphism. Okay, just I would like to say this once so that not to have confusion in future. Okay, and we have discussed the following. Last time we have proved the following theorem, that this d gamma is always isometry, orientation preserving isometry of the Lobachevsky plane. And we have proved the following, that d gamma is hyperbolic unless gamma is homotopic to a neighborhood of a puncture. And otherwise, the gamma is parabolic. If gamma is homotopic to a neighborhood of a puncture. Actually, last time we always speak only of simple closed curve, but actually it is not hard to see that the proof which was given last time, it actually works for any element of the fundamental group. Any element which is not unit. All the same arguments work as well. And in fact, we have this theorem. So parabolic are, if we consider only simple closed curves, then we have only, we can go around the puncture only once. But if we consider any element of the fundamental group, then we can go several times. Okay, it is again parabolic if our curve is not homotopic to a neighborhood of a puncture, then we are then it always should be hyperbolic. It is obvious that this cannot be elliptic, since okay, since a deck transformation cannot have a fixed point, but last time we discussed in which situations it is hyperbolic and in which parabolic. Okay, I would like to leave it as exercise just to look through the proof. And understand that it works for any gamma in P1, not only for those which correspond to simple closed curves. Okay, and now I would like to discuss once more one proposition which I formulated last time. We discussed some ideas behind the proof, but we didn't discuss proof carefully. This proposition is as follows. Now I prefer okay, proposition consists of two types. So suppose that this element let us at the moment let us distinguish between an element. I'm not very careful here, between a curve and an element of the fundamental group. Suppose that an element C of the fundamental group is chosen so that this deck transformation around it is hyperbolic. So I would like to dismiss the case of to get rid of a case of this parabolic case when we are in a neighborhood of a puncture. Then the homotopy class C contains a unique geodesic representative. No, it is not so good. I mean the following. I would like not to look for a geodesic representative for a homotopy class. I would like to look for a geodesic representative for a homotopy class. Often is not geodesic at the base point. Yes, we may try to choose. If we fix a base point, then we may try to look for a geodesic representative which is not geodesic here, but it is not natural to have maybe this curve can be shortened by a moving point x0. So I'm looking for a true geodesic representative of free homotopy class. So free homotopy class corresponds not to an element of a fundamental group, but to a conjugacy class of elements. So then the free homotopy class of curves corresponding to this the conjugacy class of C contains a unique geodesic representative. This is first claim, and the second claim, which is that if the in addition, again in this situation, if besides C contains a simple closed curve, so if this homotopy class can be represented by a simple closed curve, then this geodesic representative is again a simple closed curve. So this also should be proved. Okay, a priori it may happen that we have a conjugacy class which corresponds to a geodesic, or a conjugacy class which corresponds to some a homotopy class of curves which corresponds to some C, and it contains a simple closed curve. But when we find a geodesic representative, it might happen that we get not a simple closed curve but something self-intersection. So curve, then the geodesic representative is a simple closed curve. Okay, so let us prove carefully this proposition. Some ideas were at the end of the previous lecture, but prefer to have a precise proof. So, okay, step one. Suppose that we have so let us prove existence of a geodesic representative. Okay. We take this Lobachevsky plane, which is the universal cover of S, and we take the deck transformation corresponding to C. It's hyperbolic, hence it is a shift along some line, straight line in Lobachevsky plane by some by some distance. So we shift by some distance, and our okay. And now let us look on 2 points which are on this precise distance. Then this segment, after the universal cover, is factorization by all deck transformations. This segment goes to a closed geodesic, maybe with self-intersections. It may happen that it is with self-intersection, since, but it is closed geodesics, and this is just closed geodesic representative. So we have no problems with it. This is more or less trivial. And this closed curve corresponds to this particular homotopy class, since once we go around it, its lift goes from here to here. I do not take care about base point, since we are working with homotopy classes, with free homotopy classes.
семейство прямых, да? Как вы выбрали одну?
Yes, there are. If we consider, yes, thank you for this question. If we consider the pre-image of this particular curve, then we get a system of lines, actually of infinitely many lines, and for each of these lines, this is a deck transformation corresponding to some element of this conjugacy class. So we have pi1 of surface which acts on the Lobachevsky plane. We have all pre-images of this curve, but different pre-images can be taken to each other by deck transformations, other deck transformations, not about this curve, but
Сейчас, я чуть не уловила.
Нарисована кривая геодезическая, а не прообраз кривой, нет? Вот эта вот кривая, она
no. This is yes. If you would like to have here true straight lines, then this is geodesic.
Нет, у нас есть гиперболическое движение, а мы проявляем для какой-то одной прямой. Вот мы ее нарисовали, она одна.
Сейчас, я просто...
Правильно? Да, там, где
Я думаю, гиперболическое движение, как устроено, оно вроде это компенсирует в конце...
Нет, это сдвиг вдоль прямой. Гиперболический элемент в группе движений – это сдвиг вдоль прямой. If we take other elements of the same conjugacy class, we get shifts on by the same distance along other pre-images of this particular curve. So the picture is like that.
Прообразы этой кривой. Тут не нарисован. Ну, сейчас.
Yeah,
рисуем прямую, для которых сдвиг, и рисуем прообразы. Это разные.
Pre-images of this curve are exactly those straight lines for which there is an element in this conjugacy class. Okay.
They are not parallel, yeah?
Geodesic. Yeah, we take geodesic representative, and now all its pre-images are obtained from this one by actions of fundamental group. So all shifts along these pre-images are conjugate to this shift with respect in this group.
But by shift and this like main line, you mean the whole transformation, not only its like restriction to the line, but
no, the whole transformation, the whole hyperbolic shift of.
But you draw only one line.
Yeah, other points shift by just other, and it is important thing that all other points shift by strictly greater distances. So it is not in Euclidean situation. If you make a shift, then all points move by the same distance. In hyperbolic situation, if you shift along a line, then first of all, this is shift along a single line, not along several parallel lines, but along a single line. And second, all other points which are not on this line, they move by greater distance.
Может быть, если вы там нарисуете любые углы, то станет, в общем, то это бы ответил на мой основной вопрос. Возможно, не так реально.
А где прямая?
Ну что, это прямая, она перпендикулярна окружности.
Well, this is usual conformal model, and of course, yes, these are circles which are orthogonal to the absolute. Yes, this is only existence.
But the other points move along lines also, yeah?
They move not along straight lines. They move the other points move along such circles in conformal model, which are equidistant lines for this particular line. So no other point is moved by straight lines, straight line. So these are in this conformal model. These are just circles, which are not orthogonal to the absolute. Okay, the existence. And before proving uniqueness, let us discuss now why this curve. Let us prove the second part.
Why is the image closed?
Well,
why is the image of this line closed?
since in the group of deck transformations by which we take quotient, there is a shift by by this line. So this particular shift makes it closed. Or if further factorization make it maybe intersection or something like that. But definitely we still have. Yes, since if we lift this, then we go from. Yes.
Мы рассмотрели сдвиг до нее.
Yes.
Дали задачу геодезическую.
Yes. If we take the lift of this, okay, this geodesic is gamma.
Геодезики пока нет, у нас просто есть кривая. Когда на существование.
No. We have already this. We start with shift. Okay, we start with this class in pi 1. We take the corresponding shift. We take this segment and we look on its image here. It is closed and it is geodesic. Let it be gamma. Now let us prove that gamma represents the same class. Actually, this is not even not. It cannot be true since it's not a correct statement, a well formulated statement. Since gamma, okay, if we speak of fundamental group, we must speak on some base point and so on. But for me, it is important only that gamma represents the conjugacy class of gamma the conjugacy class of C. And so I may forget about base point. I may choose base point as it is convenient to me. Let us choose the base point so that it is the image of this particular point under our projection. Then the lift of gamma here is exactly this gamma tilde is exactly this segment. This means that the deck transformation corresponding to gamma is the deck transformation that takes this point, start point, to the finishing point of our segment. Hence, it is the C. Two deck transformations, if they coincide at a single point, then they coincide everywhere. So, hence, this the homotopy class of gamma is exactly C. Exactly C is since we choose after we choose carefully base point. So, the true statement is that we are in the conjugacy class of C. Okay.
I'm sorry. Why do you call yellow things circles?
They are circles in conformal model. They are not circles in Lobachevsky plane.
Okay.
In Lobachevsky plane they are equidistant, but if we take the Euclidean conformal model, usual Poincaré model in disk,
okay.
or in half plane, then there's true circles in this model.
Okay.
I mean usual circles in the plane.
Not orthogonal to the.
Not orthogonal to the absolute. Yeah, straight lines in Lobachevsky geometry are circles orthogonal to the absolute. Circles in Lobachevsky geometry are circles not intersecting the absolute. Equidistants are circles that intersect the absolute but are not orthogonal to it. And also we have horocycles, which are circles tangent to the. So all these standard lines are circles in this particular model. Of course, if you take Beltrami-Klein model where this projective model, then by no means they're circles. They're something different. Okay, now next step 2. Let us prove that if not gamma, if this C, this class contains, can be represented by a simple closed curve, then this particular gamma is simple closed curve. If C can be represented by a simple closed curve, then this particular gamma which we have construct is a simple closed curve. Let us prove this. Okay, suppose that this gamma is not a simple closed curve. Then there are 2 points in gamma tilde. Well, there are 2 points here. Some point maybe x and y, which go to the same point below. Yes? Okay. And No. I want first to prove that it is simple closed curve, provided that C contains a simple closed curve as a representative, and only then I will prove uniqueness. Okay. Okay, so since this x is given to this y by since if x, and let us denote this projection by p. So if p of x equals p of y, then there exists a Dex transformation which takes x to y. This is another Dex transformation. Then there exists some Dex transformation corresponding to some element of the fundamental group, such that this Dex transformation takes x to y. This Dex transformation again can be hyperbolic or parabolic, and we have 2 cases. Case 1, that this dA can be again shift along the same line, and case 2, that it is not. Okay, so case 1, that dA, let us denote this line by L. dA is a shift along L. Okay, look, DC is shift by some distance. dA is also a shift by some distance. These 2 distances can be their ratio can be rational or not. If the ratio of, okay, let dA is shift by some distance p and q, and dc is shift by some distance r. If q over r is not rational, then we get a contradiction. Why? Since our group contains a shift along this line by one distance, by distance q and by distance r, hence it contains shift by any their integral linear combination, since we may perform these shifts in different order, and hence the orbit of any point on this line is dense on this line. So we have no discreteness. This is not a covering. This is something nasty. So this is contradiction. Since the orbits are dense in L. And if the ratio is rational, then actually, okay, we may more or less replace this dA by some combination of this dA dc, and to obtain that r is just divisible by q, that r is integral times q. More or less, okay, we may normalize our metrics so that these are just two integers, and we may take their great common multiple. I'm sorry, наибольший определитель. Great common divisor, and this great common divisor can be obtained as a linear combinations of this q and r with some integral coefficients. Hence, we may replace in dA by some another shift by some combination of dA and c. We just, in this situation, we get that dc is a power of some, okay, let it be dB, a power of some shift which already belongs, is a deck transformation. And let us understand why such situation is impossible. I would like to draw it once more. Once more, we have this line, and we have some shift, and the power, or some power, where k is greater than 1. Yes? If k equals 1, then we just have a equals to c, and these 2 points are just the end points, and no problems arises. So actually this means that gamma is geodesic, which is passed several times. So in particular, actually, we have a problem which I gave to you to try to solve, that the fundamental group, that the homotopy class of a simple closed curve is always primitive. And actually, if we know this, then we are done. And in fact, now it is what I'm going to prove. Well, suppose that we are not in this case, and let us. Suppose that we have this case that our DC is some power of some other deck transformation. Let us. Our assumption is that the homotopy class C can be represented by a simple closed curve. Let us consider this curve delta. It is not geodesic, it's just some curve. And consider its pre-image. We may pre-images of delta go in some neighborhood of pre-images of gamma, since they're in the same homotopy class. Okay, look, if you have
the problem is that gamma is delta.
No, gamma is geodesic and delta is not. I would like to say that if delta is simple closed curve, then gamma should also be a simple closed curve. I mean the following, that if we start at the same base point and go in S, if we go along one curve and go along the other curve in the same homotopy class, yes, then their pre-images here, they go, we consider lifts that again start at the same base point here. And then after we lift them, and they go again to the same point. And if we lift them further, then they again go, the second step, they again go to the same point, and so on. So the distance between, if we take a parameterization here and a parameterization here, then the distance is always bounded. We never go. Actually, we must be careful about base points, since if we take any pre-image of delta, then it can go on bounded distance from another pre-image of gamma. But we always can choose a pre-image of delta which goes on bounded distance of this particular pre-image of gamma. And so we have here something like that. This is not non-self-intersecting curve, delta.
And we can suppose that delta starts from the same base point.
Yes. In fact, it is very easy. If we have a simple closed curve, then we may achieve that it passes through any prescribed point.
Or we can just start with delta. We can start with delta, then...
The problem is that we cannot make gamma to go through any prescribed point. It is better to choose to change delta than gamma. Gamma is obtained by this particular construction, so we cannot change gamma. But concerning delta, we can change it by isotopy. By isotopy, we may achieve that it passes through this particular point x0. No problems to make that a curve passes through a point. Okay, then we have this delta tilde, and we knew about delta tilde, we knew the following things. First of all, we knew that DC takes delta tilde to delta tilde. Okay, since delta tilde has homotopy class DC, so it is again just deck transformation along this curve. Second, delta tilde, actually it follows from the first one, delta tilde is on finite distance, on bounded distance from bounded distance from L. L is this line. And now, look, let us apply dB to delta tilde. Well, the idea is that I claim that it doesn't intersect delta tilde. Since it is shift okay, since delta is simple, yeah. So the delta is obtained by taking quotient of this delta tilde by the whole group pi 1. So if we go here by P, we take the quotient of the Lobachevsky plane by the whole group pi 1. If in this group there was an element, say this element, such that delta tilde intersects delta tilde, then we had here 2 points. 2 points which go to the same point below and which are not obtained from each other by DC. DC is greater shift.
Мы доказываем случай один, правильно? Все еще кейс 1 или уже нет?
Case 1, yes.
Ну, тут нет противоречий.
So, no.
Мы взяли какие-то две точки, которые склеились.
Yes,
Взяли разные, оказалось, что если еще ближе, которые склеились, но друг вдоль этого перенос. Вдоль чего-то другого.
Ну, в дельте ничего не склеивается, она простая. Well, delta is, by our assumption, a simple, we choose it to be a simple closed curve in this homotopy class. So the only things, okay, here we have points which are taken to each other by DC. Of course, they go below, they go to the same point. But no other pair of points can go to the same points below. So we cannot have this.
Вы предположили, что есть, значит, Ростазан кривая, да?
Окей.
Вы сказали, что ДЦ это сдвиг вдоль чего? Вдоль нее или вот откуда у нас?
Мы дельта выбрали.
Потом
Нет.
нормировку.
Нет. Нет, дельта это.
ДЦ это то же самое, что ДД.
С это то же самое, что дельта. Дельта это кривая, представляющая класс гомотопии С.
Да.
C is a simple closed curve represented a homotopy class C. Delta is a simple closed curve in the homotopy class C. So if we take DC, the same as the delta, then these points go after P, they go to the same point. Yes? But no other pair of point of D delta, of delta tilde, goes to the same point. Okay, okay, we have this orbit, and we have such orbit starting from any point. Okay. So the statement is if 2 points A and B on delta tilde lie in the same satisfy P of A equals P of B, yes, then B equals some dc to the power m of A. Only in this situation they may go to the same point, since delta is simple. Okay? But now suppose that they intersect. Then there are 2 points. Well, suppose that it is not empty. Then there exist 2 points such that dB of A equals, oh, I'm sorry, this point should be something different, VW, okay? VW such that dB of V equals W, okay? Now we see that, but now there exists M such that this is true. Hence dB is dc to some power m. But dc equals the power of dB, and it cannot happen in since hyperbolic elements are of infinite order. So we have a contradiction. So we have a contradiction, hence we have this property. And now what is why this also lead us to a contradiction? So look, but dB is again a shift along this line by some smaller. I cannot draw them non-self-intersecting since it is impossible, and this is the claim, that it is impossible that we have this red line which is on bounded distance from L, and it goes to itself by after some shift. We have yellow line which is again a shift of red line along this line. And the claim is that they cannot be non-self-intersecting, non-intersecting each other. Now let us understand why. Well, the idea.
Сейчас, подождите. Мы поняли, что ДБ и ДЦ постепенно совпадают в одной точке.
If two deck transformations coincide in a single point, they coincide everywhere. So this is always true. If they coincide in a single point, then they coincide everywhere. This is just usual property of deck transformations. Okay, now why this is impossible? The idea is that let us take the point which is on the greatest distance from L. Let us speak on oriented distance. Okay, on one side we have positive distance, on the second side we have negative distance. Then the distance from a point, this oriented distance from a point of delta tilde to the initial line L, it is a continuous periodic bounded function. Hence it achieves its maximum at some point. Note that the maximum of on yellow, the same maximum on yellow line is the same, since they are obtained from each other by a shift. And in the same way, take a minimum here, and we have this minimum. We have periodic number of minimas and of maximas. Just choose some of them. Well, okay, and now the idea is that let us take here some two points on the absolute, and let us go from this point to this particular point. Let us first go orthogonally to the original line L, so that we become further and further from it, and then we just Okay, we may just go orthogonally and look where we meet the absolute. And here also let us go orthogonally and meet the absolute. And here in between let us move along delta tilde. Well, now we get this blue line. And now blue line must intersect yellow line. Since this is usual topology of a disk, since we have 4 points in such order, blue, yellow, and we must have this intersection. So blue line intersects the yellow line. And this intersection cannot be on these two rays, since they're too far from the original line. So we see that we get a contradiction, and this case is not possible.
Проще расскажешь, что он почти индексом пересечения нашей кривой, самой собой.
Индексом пересечения для дельта?
Для большой.
Ну, 0. Индексом пересечения всегда 0. Геометрический индекс пересечения всегда. Но геометрический индекс пересечения вообще это то, что хорошо определено все-таки. Не, ну можно определить для произвольных кривых, мы определили, да, уже. Ну, 0, да.
А как может быть 0 для кривой, которая непростая?
А мы вообще не определяли для кривой, которая непростая, но можно. Ну так же. Да, не, на самом деле надо аккуратнее, надо взять 2 копии и все-таки считать только пересечение одной копии со второй.
И
он всегда 0. Вот, индексом пересечения всегда 0. Не, ну может быть можно определить как-то по-другому для самопересекающихся, чтобы он был не 0, но я так сходу не знаю. Вот. Okay. So we have handled this case where dA is a shift along the same line. Now, okay.
Но индекс пересечения, он имеет смысл в том смысле, что на неориентированной кривой он может быть единица, если по лентиметру пройтись.
Нет, по модулю 2 на неориентированной там, наверное, имеет смысл, да. Но на ориентированной мы работаем с ориентированными поверхностями, у нас всегда индекс самопересечения всегда 0. Вот, там просто ой-ой-ой. Well, let us proceed. So, case 2. Case 2, that dA is not a shift along L. So it is either a shift along along some other line, or it is a parabolic element. It's not a shift along L. Okay. Let us again draw a picture like that, and we will come to a contradiction in a similar manner. Well, maybe it's better to draw it from the beginning. Let us to draw a picture. It is better to consider. Let us assume that dA is a shift along some line, another line. But In fact, it's not so important. Okay. Okay, let us once more. Let us look on this L. It is more convenient to me just to draw it as a diameter. It is not a restriction. And we have again choose a simple closed curve delta, which is in the same homotopy class C, and this delta goes on some bounded distance from L, and it is taken to itself by some shift dc. Now on gamma we have 2 points, this x and this y, which are taken to each other by some another shift. Yes. This means that we have some standard line, either a horizontal or an equidistant, depending on whether this dA is hyperbolic or not, which passes through x and y. And dA is a shift along this is a shift. Okay. I draw a case of a hyperbolic, but similarly we can consider the case of parabolic. Note that there are two situations, either this one, or we also can have a situation like that this dA is a shift along a line which intersects with L. So we have two possibilities. No. I just would like to say that. Okay, yes. There are no such possibility. In these possibilities, it is an easy. The distance is monotone here, the oriented distance. So we cannot be twice on the same. Yes, this is what we cannot be twice on the same equidistant. If the line intersects, then we cannot be twice on the same equidistant with respect to this line. So no shift along line M may take a point on L to itself. So this one is forbidden. So we always have a situation like that lines do not intersect, and that's it. Okay, and we would like to say, but on the other hand, if we consider this delta tilde, there should not be 2 points on the delta tilde, which such that one goes to another by this shift dA.
And why did we say that the same thing here? We say that the shift along the A it shifts L to itself, right?
No, no.
Do we know that?
Now not. It only shifts this point to that point.
Okay, and how did we get here that it should take?
Here there are no 2 points such that it takes one to another. But here just one point x is taken to another point y. I'm sorry if I get a page at home and
Я просто как бы принимаю.
well.
Идея вроде бы проверять, кто прямой.
Yes, dA. Indeed, let us look what dA makes with dC. Yes.
Сейчас, можно нельзя проще. Нельзя разве сильно проще сказать. Вот у нас x переходит в y, да? Тут точка левее x. Сейчас или. Нет, прям.
Well, dA takes dC. Well, it is obvious. dA takes dC to some line, not dC, but dA takes line L to a line which
Intersects L.
intersects L. Yeah, dA takes L to some line like that. Okay, this is dA of L. Okay. And then we may also take dA of delta tilde. Well. We apply the same dA to delta tilde. Delta tilde is some the lift of this simple closed curve, which is on bounded distance from.
dA of L, наверное, должен пересекать несколько раз.
No problems with it. Может, что дважды пересекать? Нет, ему не надо. У нас единственная пара на L, которая переходит x, переходит в y. Все.
Для прямой не могут пересекаться.
Если мы применяем dA, то единственное, что мы знаем, что x должен перейти в y. Поэтому L должна перейти в прямую, которая пройдет через y. Вот больше мы ничего не можем сказать. But these two lines are intersecting. And now, intersecting lines on Lobachevsky plane, they are on infinity, they are very far from each other. So if we take here the idea is that if we take here this dA of delta tilde, then if we look on it in conformal model as on a curve on a plane, then its endpoints are just these 2 points. Since the metric becomes the distances become very the metric becomes very large near absolute. We have this the metric is like that. 1 minus x squared minus y squared. So if we are very close to absolute, then this denominator is very huge. And hence, in usual Euclidean metric, this line just goes to, it has endpoint on the absolute. In this particular point, exactly at the endpoint of the corresponding line. And this red line has an endpoints here and here. And again, the same argument says that delta tilde and dA of delta tilde must intersect. And this is already a contradiction, since now on delta we have 2 points which are taken to each other by dA. But 2 points, as in the previous case, 2 points the only way, situation for delta tilde. If 2 points are taken to each other by a deck transformation, then this deck transformation is a power of dc. So hence dA must be a power of dc, which is not so, since we assume that dA is not a shift along the same line. So yes, this case is handled in the same way. Oh, I'm very sorry. I have wasted plenty of time here. We proceed as following. I will prove uniqueness only in case of simple closed curves, and I hope this will be as a task for you in general case. Just I would like to save some time on this. So uniqueness in case of a simple closed curve, so general case and exercise. Okay. For simple closed curves, it's very easy. Well, suppose that we have two geodesic representatives in some homotopy class. These are C and this is gamma and delta. Yeah. Then both of them correspond to some shifts along some okay, I claim that any geodesic representative is obtained by such construction. Choosing some pre-image. Okay, we start not with the homotopy class, but we start from a conjugacy class. Yes. So if we have conjugacy class of in by 1 of S, then we may choose a particular homotopy class DC and consider such geodesic and consider such shift. Okay. I claim that any geodesic representative can be obtained. In this construction, we have arbitrarily choice. This choice of particular homotopy class inside this conjugacy class. But I claim that any geodesic representative for our conjugacy class is obtained in such a way. Look, okay, if we have a geodesic representative, let it be some epsilon, then let us look on the universal cover, choose a preimage, one of the preimages of epsilon, one of the lines which are preimages of epsilon, epsilon tilde. And okay, deck transformation along epsilon is a shift along this line, and this shift must be conjugate to DC since since epsilon lies in the same free homotopy class. So it is conjugate to DC. So the epsilon is conjugate to DC in pi 1 of S. Yes. Well, actually, okay. First of all, we need even to restrict ourselves to this case. It is true in any case. Since it's conjugate, then this one and that one are taken to each other by some isometry in pi 1 of S. Hence, below they are the same curve. That's all. So in fact, this is an obvious statement. I wanted to tell you a harder proof, but actually this is very easy. Okay. So we finally have proved this theorem. It requires some accuracy, but now it's done and we are free to use it, and it is very convenient that we always can take speaking on homotopy classes of curves, in particular of simple closed curves, we always can take just representatives, geodesic representatives in some hyperbolic metrics, and the situation becomes much simpler. And another very important but very easy thing which I must say here, that again proposition, that geodesic representatives are always in minimal position. So representatives are always in minimal position. Why? Since there are no bigons on Lobachevsky plane. We have this bigon criteria. What I mean precisely, if we have two homotopy classes of a simple closed curves, then we know that, okay, we may try to minimize by homotopies of these curves, we may try to minimize the number of crossings in transversal position. But we may take just geodesic representatives and count number of crossings there. The claim is that this is a minimum. Why? Since we have a bigon criteria, if two curves are not in a minimal position, if not in a minimal position, then there should be a bigon. Bigon is an arc of one of this curve, an arc of the second of this curve, and what is the most important, a disk here. Yes? With this too. Okay, since this is a disk, if we have such situation on our surface, we can lift it to the universal cover, to Lobachevsky plane. And since this is a disk, then the lift is also a disk, since it is contractible, so it lifts just to the same picture, to a bigon in Lobachevsky plane. But if these two curves were geodesics, then in Lobachevsky plane we would have two straight lines with a bigon between them. This never happens. So this is impossible. So since we have no bigons on Lobachevsky plane, we have this simple observation, simple but very important, that in fact, why it is so important? In fact, we have proved a very interesting fact, which is by no means obvious. That, okay, we knew that we can put any two simple closed curves in minimal position. But it turns out that we can put all pairs of curves in minimal position simultaneously. So if we take geodesic representatives for all curves, then any pair of curves is in minimal position for the same set of representatives. We need not to fit representatives to particular pair of curves. We needn't find some particular representative for a particular. Actually, this proposition says us that more or less, to be honest, in papers on mapping class groups, if you on this topic and something around it, people never distinguish between curves and isotopy classes of curves. They just write curve and they mean isotopy class of curves because it's just shorter. And propositions like that allow to do such things. Okay, now let us have a 10-minute break. I am very sorry. I told you only about half which I would like to talk today. I think that we proceed with something like a second lecture.
есть его не нужно включать просто.
Все, спасибо большое. Well, the next thing which we are going to discuss is the space of all hyperbolic metrics on a given surface. So we have already, I have already shown that for a closed surface we have at least one hyperbolic metric, and our next goal is to understand first what corresponds, what happens in the situation of punctures, and also even in closed case, I would like to understand what is the space of all. We would like to understand the space of all hyperbolic. Again, let us be precise that finite area and complete matrix on the surface, which is genus G surface with n punctures, but okay, we would like to understand these metrics up to some equivalence relation. Now we would like to consider them up to isotopy. Since if we just consider all metrics, then there are huge infinite dimensional family of them. It is not so. We can isotope any metric in a arbitrary small neighborhood and get another metric, but isotopic to the initial one. So just to study all metrics, it's too huge set. But we would like to study them up to isotopy. And another possibility, as I have already told, is just to study up to isometry. We have already discussed this difference. Well, for instance, if we have such surface, well, then it may happen, then say, okay, I just write down something that this length is 3 and this length is 4. Yes? And in another metric, vice versa. This length is 3, 4, and this is 3. Okay? And then this metric, I mean a length of a geodesic representative of a curve. Then this metric can never be taken to that one by an isotopy. I mean that this is the same surface identified by just this. But it may happen that this metric is taken to another one, say by such rotation. So that in fact they can be isometric. So it is this difference, and this difference is just by the difference by mapping class group. So this difference is very important to us. But now let us focus on the question of metrics up to isometry. First of all, isotopy, sorry. First of all, I would like to say that of course, yes, to introduce hyperbolic metrics and to study them, it is very convenient to cut the surface along closed geodesics. So the approach will be like that. But once we cut a surface along a closed geodesic, what we get is not a surface with, okay, if we consider some hyperbolic metric on a surface, and we find here a closed geodesic, and we cut along it. Okay, we may cut in two ways. We may just delete this surface and obtain a non-compact surface, which is homeomorphic to, in this case, to a genus 1 surface with two punctures. This is first possibility. The second possibility, we may duplicate this boundary circle and obtain a surface with two boundary components. In the first situation, the metric, we get a hyperbolic metric on the obtained non-compact surface, but it is not complete. So starting from complete metric, we go to non-complete one. So this is bad operation. It is not convenient to work with non-complete metrics. I don't want to do this. So the good operation is to cut and duplicate the boundary component. But then I would like to work not only with surfaces with punctures, but also with surfaces with boundary components. So I would like to say which hyperbolic matrices I would like to study on surfaces with boundary components. So in fact our object will be more general, not just surface of genus G with n punctures, but also with B boundary components. And now I would like to study, let us draw something like that. So we have several boundary components, we have several handles, we have several punctures, something like that. And I would like to study hyperbolic matrices on this guy. But these matrices, these metrics, again, I would like to have that they are finite area. Complete. But also I always want the boundary components to be geodesics. So this is a requirement, this is a restriction. I study only such metrics that boundary components are geodesics, and in fact I would like to have here geodesics of prescribed lengths. So I assume these lengths to be as additional data. So I am given not only a surface, but I am given a surface with B numbers. B is number of, and these numbers are assigned to the boundary components of this surface. And just now I would like to study these numbers must be strictly positive, and now I would like to study only such metrics that they are finite area, complete, and boundary components are geodesics of their prescribed lengths. Oh, sorry. Okay, and yes, and first of all, it follows from the Gauss-Bonnet theorem, which we have discussed last time, that if we take area of any hyperbolic metric with these properties, then it is minus 2 pi by Euler characteristic. Yes, and this means that it is 2 pi times for 2g minus 2 plus n plus b.
Стоит вместо S написать SGBN, потому что наверху, то есть S
Окей. So hyperbolic matrices hyperbolic matrix can exist only if the Euler characteristic is negative, and this corresponds to inequality to G plus N plus B greater than 2. Sorry. Yes, so we may have, if we have a sphere, genus 0, then we must have at least 3 punctures and boundary components. If we have torus, then at least 1 puncture or boundary component. If we have genus greater than or equal to 2, then everything is okay and no further restrictions. So we are in this situation, and we start with the easiest case. Yes, and also one important remark. One important remark is here, okay, for a surface with boundary components, I told you what is I have told you what is requirement for metric, but I have not told you what is a requirement for isotopy. So these things there are 2 possibilities. Just we may consider up to all isotopies, or we can consider up to isotopies which are preserving the boundary, which are trivial on the boundary. And though it may, at the moment I prefer to consider them up to all isotopies. It is more convenient now. Yes, and another important point, that suppose that we are in this situation, with boundary components. Then, unlike in all previous cases, the universal covering is not the whole Lobachevsky plane, it is some region in Lobachevsky plane. Since we come to this, to the boundary, and after them there is no covering, okay? But this case can be easily reduced to the case of a closed surface. So all the results, those results that on these hyperbolic and parabolic elements and geodesic representatives and so on, everything that we proved last lecture and now and today, all these things can be easily transmitted to the case of boundary component just by the following observation. If we have a surface with several boundary components, then we can take the double of it. We can take second surface with the same matrix and just glue their boundary components along identity isomorphisms. And what we get? We get now a surface of some higher genus with a greater number of punctures, but now this is true hyperbolic surface without boundary. This is why the lengths of the boundary components are the same, so there are no problems with it, and now for that surface all the results are true, and hence they're also true for this surface with boundary. Okay, now let us...
Yeah, if we glue to this, things will obtain a genus 2 surface. If nothing inside, just 3...
No, we have...
If nothing, nothing, then we'll have a genus 2.
Yes.
And if we glue torus with one boundary component with itself, again genus 2.
Again genus 2, yeah.
The minimal really like...
Yeah, so certainly the Euler characteristic is additive. So if we glue something of negative Euler characteristic, we always get something also of negative Euler characteristic.
Потому что, вот, допустим, взять какую-то кривую отсюда, почему, если мы смотрим ее как кривую удвоенной, почему она не будет, язычки не будет пересекать границы?
Yes, thank you for this question. A good question is why, indeed, if we duplicate something and, for instance, find okay, it's double, yes? And find geodesic representative for some class here. Yeah? Why it doesn't cross? Why it doesn't go outside? Why it doesn't cross? The idea is that all curves are in minimal positions. So if we go, if it is possible to realize this curve inside the original surface, then the geodesic representative is also inside of the original surface. So we never have some such problems. Okay. So let us start. The easiest case is the sphere with 3 of the, genus 0 with 3 boundary components. And before, so we would like to consider situation like that. And the claim in this situation is that once we have prescribed edge lengths L1, L2 and L3 of positive length, then claim is that there exists a unique up to isotropy hyperbolic metric on the sphere with 3 boundary components with geodesic boundary and prescribed lengths. So there exists a unique up to isotropy. Uniqueness, of course, is up to isotropy. Geodesic hyperbolic metric on this S03. This 3 is not a dimension, it is number of boundary components. With geodesic boundary components of prescribed lengths.
But then this surface is some isotopes.
Well,
Are there any isotopes on this?
yeah, there are all of the, okay, assume that this is a ribbon surface. I just take and rotate it by some. We always have isotopies. We always have plenty of isotopies just with supporting any small disk. So we always can just. Нет. У нас есть разные метрики, но метрики можно реализовать здесь по-разному. Вот геодезическая может идти вот так, а может идти вот так. Как бы мы... Как сказать, у нас метрик вообще очень много, то есть нет, как раз существу она одна. Вот это аптоизотопия означает именно что... Okay. And to start with, we need to go some... we need to discuss some easy things in hyperbolic geometry, in usual Lobachevsky geometry. And these easy things are right-angled hexagons. So what do we need to know about right-angled hexagons? On Lobachevsky plane. If we have, I mean that we are interested in hexagons with all angles right. So once we have such hexagon, we have its edge lengths, which I conveniently denote in such order: x1, x2, x3, and y1, y2, y3. And claim is that for these x's and y's we have cosine law and sine law. Cosine law, I always forget signs, so it's better to look. Hyperbolic cosine. Once I speak in English, it's better to use English notation. So this cosine law, and also, okay, 5 other cosine laws in the same spirit. And sine law is that hyperbolic sines of x's go to hyperbolic sines. Their ratio to hyperbolic sines of y's are equal to each other. Okay, why this is true? This is true since, in fact, there is no difference between such situation and a triangle. Where if we have two lines, straight lines in Lobachevsky plane, then in vector models, in a vector model, they are plane sections of the hyperboloid. So one line L is sectioned by some plane alpha, and another line M is sectioned by another plane beta. And the plane, this is in pseudo-Euclidean space with standard scalar product minus x0, x0, minus xy, minus x0, y0. These are different y's and x's. Okay, and the plane can be given by its normal vector. Normal vector, of course, in this pseudo-Euclidean sense. So we have some normal vector n1 and n2 are normal vectors for alpha and beta respectively. Note that these normal vectors are space-like. So they have positive scalar squares. Since if they are time-like, then these planes will not intersect the hyperboloid. Once they intersect the hyperboloid, the vectors are space-like. And okay, if we were in usual Euclidean situation, then the cosine of the angle between these two planes can be computed as we take scalar product of their normal vectors and divide by their lengths. Here we may proceed in the same way, and we may look on such value. Well, this n is just square root of n, which is well defined since n is space-like. And if we look on this thing, then up to sine, is if we change sign of n1 or n2, then we have obtained some sign here. But up to sine, we obtain the following. It is for these two lines, we have three possibilities. We have here, so this number is cosine of phi if L intersect M at angle phi. If they intersect at angle phi, then it's just cosine phi. If they are what is called convergent or parallel, if they intersect on absolute, then it's 0 in this situation, and it is hyperbolic cosine of the distance in the case of divergent line. Here we have some distance rho. So in the case when two lines do not intersect, the hyperbolic cosine between them acts the same role. The hyperbolic cosine of their distance plays the same role. Oh, so sorry, it is not 0 here, it's 1 here. The same role as cosine of length of angle between them. So if usual cosine laws for a triangle is when we have x1, x2, x3 here, and here we have some angles. And instead of cosine of y, we have here, oh sorry, if it's x3, then of course here is y3. It should be symmetric. Here instead of y3, we have cosine of this angle, and we get usual cosine law in Lobachevsky geometry, but this is the same claim. Indeed, it just maybe I will not speak on this, but it is a good exercise just to prove it if you don't so this is exercise to prove these two if you don't know them. But okay, the proof is as for usual cosine law for trigonal angle or for spherical triangle or for Lobachevsky triangle, all these proofs, and for hexagon, all these proofs are go the same line. In fact, in vector form, if we write everything through these normal vectors to lines, then this is the same. These are just the same facts. Okay, so we have this formula, and this formula says us that if we have a hexagon of this such right-angled hexagon, then the most important for us is this cosine formula. And if we look on them, we understand that y's can be computed from x's. It can be uniquely computed. So y1, y2, and y3 can be uniquely computed from x1, x2, and x3. So if we have positive x1, x2, and x3, then there is only one right-angled hexagon with the prescribed axes. But a good question is, do it always exist? And a claim is that for each positive axis there exists a unique up to isometry right-angled hexagon with the prescribed these side lengths with the prescribed s1, 2, 3. We need to prove only the existence, since the uniqueness follows from this cosine law. Okay, for the existence, just look. It is very easy. Just look on what restrictions. Well, these are 3 lines, and we would like to impose 3 restrictions on. No, not these 3 lines. I would like to consider these 3 lines. And I would like to impose restrictions on their normal vectors. They are inner normal vectors in vector model, but I just draw them here. Okay, it is not hard to see that in this situation, if they look like that, then in fact scalar product is negative. So we get minus cosine hyperbolic of this x2, not plus. Okay, so I would like to have if I take here unit normal vectors, unit again with respect to the pseudo-Euclidean scalar product, then I would like to have the following gram matrix of them. I would like to have units here, and here minus cosine hyperbolic of x3, here minus cosine hyperbolic of x2, and here minus cosine hyperbolic of x1. Well, and an easy fact is that this matrix is non-degenerate and it has signature 2, 1. So if we consider bilinear form, symmetric bilinear form with such matrix, then its positive inertia index is 2 and its negative inertia index is 1. This is very easy to see, just if we denote cosines of x's by C1, C2, and C3, then they are greater than 1. And our matrix is like that. It is just 1, 1, 1, minus C3, minus C2, minus C1, and symmetric here. And if we consider, as in usual Jacob's method, such minors, then we have delta 1 equals 1, delta 2 equals 1 minus C3 squared, and it is negative since C3 is greater than 1. And delta 3 equals, okay, it's 1 minus 2 C1, C2, C3 minus minus C1 squared minus C2 squared minus C3 squared, so it's definitely negative. So we see that we have one change of sign, so the positive inertia index is 2 and the negative inertia index is 1. And this means that so the corollary is that in pseudo-Euclidean space of signature 2, 1, there exist 3 vectors with this particular gram matrix. There exist vectors n1, n2, and 3 with such gram matrix. Well, now look on the lines given by these 3 vectors. So we take planes orthogonal to these 3 vectors. So alpha 1, alpha 2, alpha 3 are planes orthogonal to n1, n2, and n3 respectively, and Li is the line obtained by intersecting this with the hyperboloid. Yes, and this is non-empty since vectors are space-like. So, and these lines satisfy that their distances are exactly x1, x2, and x3. This is just because we have such matrix. So we have found such 3 lines with the prescribed distances. This can be done geometrically or in such way. All things are possible. Okay, and now we immediately have, starting from such hexagon, we immediately see a hyperbolic metric on the sphere with 3 boundary components. Namely, if we are given 3 lengths L1, L2, and L3 of the boundary components, if we are given L1, L2, and L3 positive numbers, then let us take x1 equals to L1 over for x1, x2, and x3 we take halves of these lengths, and we find this hexagon, right-angled hexagon with L1 over 2 here, L2 over 2 here, and L3 over 2 here. And now we double this hexagon in the following way. We take two copies of this hexagon and glue them along the identity isomorphisms of these three sides. And these three sides remain unglued, but since the angles are right, when we glue two such angles, we have no singularity on this point. We have usual boundary points. So, and the numbers, the boundary components become geodesics. So we have two hexagons here, or something like that, and topologically it is a sphere with three boundary components. We have no singularities, we have usual geodesics here, and the lengths are as prescribed. Well, the only thing is why it is unique up to isotopy. First, let us prove that it is unique up to isometry. And why? The first, uniqueness up to isometry. Up to isometry. In fact, we need to prove that given any metric on hyperbolic metric on the sphere with three boundary components, with the geodesic boundaries of prescribed edge lengths, we can cut it into two rectangled hexagons like that. Okay? So suppose we have any metric on S03. Let us double it. Then we get, okay, it is not very easy to draw, but if I double it, I double it by means of the inversion. I double it adding the okay, so we get something like that. Okay?
Ну, у нас вот то
Ну, короче, вот это на нас смотрит. Да. Ну,
sorry, we shouldn't have this one.
да. Ну,
Yeah?
видимо, да.
But it's very.
Ну, это такая задняя стенка, там, кстати, она есть.
Да, она есть.
Yeah,
Нет, ну, если вот так нарисовать, то надо просто думать про то, что вот мы смотрим на все, нет дырок, когда мы смотрим на это. Можно нарисовать верхний.
Вы хотите сферу с тремя ручками нарисовать, подклеив две
No, с двумя.
Там две, ну, ручки там две.
I would like to have two handles, genus 2, and
А
not.
вы не хотите вот эти штаны перерисовать как, ну, как расческу такую? Тогда все будет
О,
понятно.
кстати, да, это нормально.
Да. Это правда.
Здесь какие-
Oh, yeah, so sorry. Indeed, it's
Надо
trivial.
просто три таких этих нарисовать.
Yes, I'm sorry for that. Yes, it's much easier to do this like that. Well, okay, and suppose we have this, and let us consider. Let us consider such simple closed curve of this particular topological type, in this particular homotopy class. What can I say about this curve? I can always find a geodesic representative of it. Yes? And this geodesic representative must have a single intersection point with this geodesic and a single intersection point with that geodesic, since geodesic representatives are in minimal position. This particular representative which I have drawn have 1 point here and 1 point here. This is minimum, so the geodesic representative must also have 1 point here and 1 point here. So I draw, now suppose that this one is geodesic representative. Second, I claim that it is orthogonal here. This is just because of symmetry. We have a symmetry. It is orientation reversing, but it is an isometry that takes this metric to itself. If the geodesic representative was not symmetric with respect to this symmetry, then we would have two geodesic representatives in the same homotopy classes. This one and symmetric one. This is impossible. So here we must have symmetry, and it must be orthogonal to the boundary components. Now look in a similar way what I have found. If I draw the original surface with 3 boundary components, I have found a geodesic which goes from one boundary component to another boundary component, or which is orthogonal to these boundary components. And okay, I have found such geodesic. Now I can find such geodesic for another pair of components, for other 2 pairs of components. But okay, I would like to get a picture like that. But a natural question is why this, what happens if I, for at least these 2 geodesic representatives, come to the same point, or they intersect. So is it possible that first of all, it is impossible for them to come to the same point, since in the Lobachevsky plane we have a single geodesic which is orthogonal to the absolute to the given geodesic. So if we start from the same point, we can't go into different directions. But a natural question is why we haven't some nasty situations, say like that. Why they do not intersect?
You can choose the representatives there that do not intersect.
Yes, because we can choose here 2 representatives, well, just as I draw here, which do not intersect. And hence, geodesic representative will also not intersect. And this is why, okay, we get such things. Okay, so we can cut along these segments, and we get 2 hexagons. But okay, we need also another fact. We need also that these 2 points are not only different, but they are antipodal. We must have that if here is L1, then we have L1 over 2 here and L1 over 2 on the other side, and the same for 2 other boundary components. And why this happens?
It's just not true.
No, it's true. It's true again by the same fact, but now we need that x's can be uniquely computed from y's. So since these blue, red and y sides are equal, then the other 3 sides also must be equal to each other. So we indeed have this. In our situations, starting from arbitrary hyperbolic metric, we have understood that it can be obtained by gluing two right-angled hexagons in these particular ways. And these two hexagons, they are uniquely determined by three numbers L1, L2, and L3. So we understand that there is a unique hyperbolic metric up to isometry. Unique hyperbolic metric up to isometry. Since we would like to have a unique hyperbolic metric up to isotopy, we must be more careful about these three lines. Namely, what I would like to have is in a sense, what we are going to prove is that now we are going to prove that the mapping class group of a sphere with three boundary components is generated by twists about boundary components. In fact, if it becomes trivial if we forget that we fix the boundary. So if we define mapping class group of considering all isotopies not fixing the boundary, then it becomes trivial. This is what we need. Since another possibility to understand it is that, okay, starting from any hyperbolic metric, we get these three: yellow segment, blue segment, and red segment. Okay, starting from another metric, we get some other three. Consider two metrics on the same surface. Just I draw it twice just for convenience. But this is the same surface, just the same object. Here we have some other: yellow, red, and blue. I would like to, I claim that they are isotopic to each other. These three, set of three segments and this set of three segments are isotopic to each other. And if we prove this claim, then we understand that the metric is unique up to isotopy. So claim, this is just pure topological type claim, that suppose we have a sphere with three boundary components, and we have three pairwise non-intersecting segments. One of them, yellow, connecting first and second component, blue connecting first and third, and red connecting the second and the third components. And we have another set of such three components, such three segments. Then this set of segments is isotopic to that set of segments. This is what we need to prove. Well, let us start with just two yellow segments. So well, yes, and I allow isotopies which are not, which do not fix the boundary. Otherwise, it is not true, of course. So suppose we have these two yellow segments, which are now, well, I draw one of them by yellow and another of them by green. And I would like to say that they are isotopic to each other. Well, in fact, we can proceed here in two ways. First way is a longer one, but we can actually transmit to the case of surface with boundaries, and here we have not curves, closed curves, but arcs which connect two components of boundary. We can extend here all the theory about Huygens and so on, all the theory about minimal position. It's actually, when I told you about this theory, I did not want to speak about all possibilities. We may have simple closed curve, we may have arcs, we may have arcs that go to punctures. There are plenty of such possibilities. Everything more or less is parallel to each other. And if I started from the very beginning with the very general case, it would be too cumbersome. But everything can be made in the same way. The only difference is that now, except for Huygens, we may have Huygens. If some two curves are not in minimal position, then we have either Huygens or a half Huygens. Here is a half Huygens. It becomes Huygens if we duplicate. And everything remains true if we everywhere say Huygens or half Huygens instead of just Huygens. And then we have, once we have theory of minimal position for arcs, we may say that two arcs are in minimal position only if we have Huygens. Let us put these two arcs in minimal position. They are in minimal position only if we have neither Huygens nor half Huygens. Suppose that we put them in minimal position and still we have a crossing, at least one crossing. Then we may compute Euler characteristic. If we have at least one crossing, then we have at least three pieces. Yes? The total Euler characteristic is -1 here. So we have at least two pieces of Euler characteristic 0. We have at least three pieces in total, and the total Euler characteristic is -1, and of course there cannot be pieces of positive Euler characteristic. So we have at least two pieces of negative Euler characteristic, and at least one of them doesn't contain this third curve. And hence, since it's of 0 Euler characteristic, the only two possibilities are a Huygens or a half Huygens. So the claim obtained by such analysis is that if these two arcs, yellow and green, intersect at least in one point, then they are not in minimal position. So when we put them in minimal position, and we can put curves in minimal position by an isotopy. Once we have put them in a minimal position, they do not intersect. Well, in fact, instead, before proceeding, I just would like to say that instead of using all this technique for arcs, in this particular case, we could just duplicate and put in minimal position the doubles of these curves. But in more general cases, it is not so convenient, so it's better to say these words and to have this technique, and actually we also will use this technique for arcs as well. Okay, but if they do not intersect, then okay, there are only two, just again by some basic classification theorems for surfaces, the only possibility is that one of the two regions between green and yellow curves is cylinder and another is disk. And those which is disk provides us an isotopy between these two curves. Okay, we have found an isotopy between yellow curve here and yellow curve here. So further we may assume that yellow curves are the same. Okay? After we assume this, we may cut along this yellow curve. So since they are the same, now all further isotopies will stabilize pointwise this yellow curve. Hence we can cut along them, and cutting along them we arrive to the following situation. If we cut this along the yellow curve, then we get here one component, yes? So we in fact we arrive to the following situation. We have a cylinder, and we have here but let us be accurate here. We have not only cylinder, but we have also these yellow segments with which come from yellow curves. We have these yellow segments, and
sorry, but on the other side, why do we have?
Only on one side, of course. Yes. I'm sorry. We have this cylinder, and we have such situation, and we have a red curve here, and we have blue curve here, and we have another red curve also here, and we have another blue curve here. And I claim that two of the initial set of red and blue curve is isotopic to the second set of red and blue curve via isotopy, which stabilizes pointwise these two segments. And again, by the same technique, I don't want to go in details, but again we can extend this isotopy to the trivial ones. Okay, I'm sorry for it takes too much time, but now, yes, and well, another important thing is that all this theory can be extended to a case when one or several of these L's equal 0. But in this case, we get not a hexagon, but it becomes a pentagon if one of them. So we may see. We can see the following situations. We may see pentagon with one vertex, 1, 2, 3, 4, 5. Yeah. pentagon with one vertex on the absolute. Here we need to be more here we need to be more careful. Of course, we do not have any lengths of these two sides. They have infinite lengths now. But okay, claim is that if we have only two axes here, one of the axes becomes have become 0. So, but claim is that such that this y is uniquely determined by x1 and x2, and this pentagon is unique up to isometry. I would like to leave it as an exercise. It is not hard that y3 is uniquely determined by x1, x2, and such pentagon is unique up to isometry. And the same happens when 2 or all 3 axes becomes 0. So I just would like to write here the corresponding corresponding pictures. If 2 of them become 0, then we have a foregone with 2 right angles, and here we have only one x, and again this one is unique up to isometry, which is trivial in this case, and we have no y's. And in if all 3, then we just have an ideal triangle, and it is a standard fact on Lobachevsky geometry that it is unique up to isometry, that any 2 of such triangles can be taken to each other. All triples of point on the absolute are equivalent to each other. Okay, and this means that all these results extend to the case of sphere with 2 boundary components and a puncture, sphere with 2 punctures and a boundary component, or sphere with 3 punctures. So in each of the cases we have considered in details the case of sphere with 3 boundary components, but in case in which of the cases sphere with 3 boundary components, sphere with 2 boundary components and 1 puncture, sphere with 1 boundary components and 2 punctures, and sphere with no boundary components and 3 punctures. In which of the situations there is a unique up to isotopy, hyperbolic metric. Of course, in case of punctures, I need to add that it is finite area and complete, as usual, and with prescribed edge length, with the geodesic boundary components of prescribed lengths, with geodesic boundary components of the prescribed lengths. So in particular, for a sphere with 3 punctures, we have no prescribed lengths, we just have 1 hyperbolic matrix, only 1. Okay, and Now the time is almost over. But now we at least may see how to get hyperbolic matrices, hyperbolic metrics, and next time we will discuss this in more details. But okay, useful fact that is that for any surface of negative Euler characteristic, which we are interested in, when there is Pans, so-called Pans decomposition. This means the following, that using if Euler characteristic is greater than, is negative, then we can find a collection of pairwise non-intersecting simple closed curves. Then there exists a finite collection of pairwise non-intersecting simple closed curves, say alpha 1, alpha n on S. S as usual is S, G, and B, such that it decomposes S into Pans. Pans are these types of sphere with punctures and boundary components, such that the total number of them is 3. Either 3 punctures or 2 punctures and 1 boundary component, and so on. Here we mean that when we say decompose, we mean that we duplicate lines along which we cut. So when we cut, we do not get punctures, but we get 2 boundary components. Here we mean, as I have told, there are 2 ways to cut. Here we cut so that we get boundary components. Here we mean that we cut so that we get boundary components. Well, how to prove this claim? Just what we need to prove is that if, first of all, it is easy to check that well, sorry. I'm afraid this is not true. I have a counterexample. If we have a torus with 1 puncture, then I think it cannot be cut into Pans. Here we have Euler characteristic -1.
Почему? Просто разрезаем по одной кривой и получаем.
Oh, yes, of course. Well, I'm sorry. Yes, of course, it can be cut. And well, yes. First of all, it is not hard to see that there are only 5 types of curves of Euler characteristic -1.
Сейчас я не понял, что говорят про торус, потому что
This is
штаны вроде там должны быть 3 компонента границы.
we have a puncture, or we have totally. These are just such generalized pans.
Значит, просто вообще нельзя с точно.
2 point and 2 boundary. Yes, but there are only 5 types of, it is easy to see from classification that there are only 5 types of surfaces with Euler characteristic -1, exactly -1. These are these 4 plus 1 puncture torus, plus 6 types, plus torus with 1 boundary component. But if we have here a boundary component or a puncture, then okay, we can cut. So the only so these two can be reduced to this. The only thing we need to cut the surface of negative Euler characteristic into surfaces of Euler characteristic -1. So the only thing we need is that suppose that Euler characteristic is strictly less than -1. Then I need to cut this surface into 2 surfaces, each with both Euler characteristics negative. If I find a curve which cuts it into 2 surfaces with negative Euler characteristic, then I'm done, since I just proceed by induction until all Euler characteristic becomes -1, and then this simple observation says us that okay, we can reduce it to only 2 points. And how to find this curve? Okay, if we have at least 2 punctures, or this can be easily proved by classification. If we have at least 2 punctures, or at least 2 boundary components, or at least a puncture and a boundary component, then we can just do like that. We can cut a piece which is a pair of pans, and the rest has also a negative Euler characteristic. If we have only 1 puncture on 1 boundary component, so if if the number of punctures plus the number of boundary component is less than or equal to 1, then since the Euler characteristic is negative, then the genus must be since the Euler characteristic is -1, then the genus must be less than or equal to greater than or equal to 2, at least 2. We cannot have if we have this genus 2, we may forget about all punctures and boundary components and just do like that. And we cut a torus with 1 boundary component. This has Euler characteristic -1, and this has also negative Euler characteristic, and we are done. After we have cut our surface into pans, we may proceed as following. I just want to draw some example. Well, I drew an example of closed surface, since it is not so okay. These are handles. So sorry. These 3 are handles, and 1, 3, 4, 5, 6 are boundary components, are curves in this collection. Now we may write here arbitrary positive lengths. Okay? And given these lengths, we may, for each pair of pans, for each surface of any of these 4 types, we have a unique aptoisotopic hyperbolic metric. And now, with the prescribed edge lengths. And now these hyperbolic metrics can be glued to each other. But an important thing which we discuss in details later is that this length is only half number of the parameters. The matter is that once we have chosen these edge lengths, inside each of these pair of points we have that three yellow curve, red curve and blue curve, which are geodesic segments between, and then they are defined by the matrix inside here. And we have so we have such reference points on this surface to antipodal, and when we glue metric on this surface with metric on that surface, we may make some twist. We obtain twist parameter which says us how to twist one of borders of this along the other. And so in fact we get here as many parameters as the number of curves multiplied by 2, since we have twist parameters and length parameters. And next time, the most non-trivial thing here is that all metrics that we get in this way are pairwise non-isotopic. So in fact we have the number of parameters is just gave us the one-to-one correspondence between the set of metrics up to isotopy and the set of R to the corresponding power. Actually we get here 6G minus 6 plus N plus B. Yes. Yes. If the edge length, if the lengths are prescribed, if they are not prescribed, then here we get additional parameters for B's. Okay, but this will be next time. Okay, I think it's time to finish today. Thank you. Не выключается.
Надо держать.
Не хочет меня переставить записывать.